To start off today's proceedings then, what I would like you to do, using your calculator and your table of differentials and your memory of last week, particularly what is it that the differential tells us about a function. A couple of questions. Number one, sketch y equals minus 5x squared. Try sketching that function. Don't need to put any figures on it, just what would it look like. You might think about where it cuts the y-axis, things like that, you know, what is the value of y when x equals 0. And then for that function, find the gradient when x equals 2. Number 3, sketch y equals 5 sine 3x. What would it look like that? Again, think about where it cuts the y-axis, and you might be able to put one figure on it that would be helpful. But what would it look like is the main thing. And then find the rate of change when x equals 0.1. These shouldn't take long. Think about what the differential tells us. So first off, sketch the curve. Well, I sort of have in my mind that I know that what a quadratic, because that's what this is, an x squared means it's a quadratic, and I know a quadratic curve is that sort of shape or that sort of shape, depending on whether the x squared is positive or negative. So I've got that in my mind, and then I think, well, okay, if I let x equal some values, that might help me to sketch it. So if x equals 0, then it doesn't matter what the rest of it is, the whole thing's going to be 0, so it must be cutting there. So I'm going to make it go through that point there, the origin. And then as x increases, x equals 1, it'll be minus 5, so x equals 1, y is going to be minus 5. So it looks as though it's going to be going this way. So if I've forgotten which curve, is it this one or this one, that tells me it must be this one. So it's going to look a little bit like that if I sketch it. It's going to hit the y-axis and it's going to curve like this. So hopefully you have something that looks a little bit like that. A parabola, which is that shape, cutting the axis at 0. Now I want to find the gradient when x equals 2. So when x equals 2, say here somewhere, I want to know what is the gradient at that point. So I could do fancy sort of things with autograph, you know, and maybe find out what the gradient is by drawing a little triangle in. However, there's a much easier way than that, isn't there? We differentiate it because the differential tells us a new function to find the gradient of the curve. So if y equals minus 5x squared, I differentiate dy by dx. I look at my table of differentials, and the rule tells me I bring the power down, multiply it by the number in front, so minus 5 times 2 is minus 10, and then I take one off the power. It's minus 10x. And now all I've got to do is if x equals 2, I want to find the gradient at that point, so I let x equal 2. So the differential equals minus 10 times 2, which is minus 20. Dead easy. if you remember how to differentiate and you remember what the differential tells us. So 3 and 4 is similar, isn't it? Sketch the curve. So I put some axes on. And I know the sine wave starts at 0 unless there's some sort of phase difference, unless I had some sort of alpha in here, or phi, some sort of phase angle, which would shift it left or right. So if it's y equals 5 sine 3x, it's going to go through the origin, and it's going to look like this. If I was asked to sketch it, something like that. I might continue at this side as well. So that's a sine wave. If it had been a cosine function, then we know that that starts here, doesn't it? It goes down like that. So a cosine function would look like that. So this is a sine function. So let's sketch it. I could work out where it cuts there, the period, because I know something about this. I'm not asked in this particular case, but just to remind you, because we have talked about this, that is the angular velocity, isn't it? And the angular velocity is 2 pi f, which is where f is a frequency. So I could work out the frequency, and if I know the frequency, I can find the period of the wave. So I could find the time it took for it to get to this point here. I could put that on with a little bit of calculation. But I do know this point, because the number 5 in front is the amplitude, so I know that's 5. So I could put that on without much hassle. But a bit more awkward to find the frequency and the period of the wave. That's the sort of thing that we did previously when we looked at wave function. It might well come up in the exam, that sort of thing. So know how to sketch waves and how to put values on where when given information. Now I'm asked to find the rate of change when x equals 0.1. Well, I'm not sure where 0.1 is along here because I don't know what this is. But I do know how to find the rate of change, because the rate of change is given by the gradient. The gradient at a point tells me the rate of change. So the rate of change is maximum here, 0 here, positive here, negative here. So the rate of change is the gradient of the curve. How do I find the gradient? That's easy, I differentiate it. So I go to my table of differentials and look for the sine function. And for that it tells me if y equals 5 sine 3x, then the differential, I look at the table, the number inside, the 3 comes out and multiplies by the number in front, that's 15, and the sine changes to a cosine, and the rest stays the same. After I've done a few, I can just write it down, it's not difficult. Now, I'm told that when x equals 0.1, what's the differential? What is the gradient? What is the rate of change? It's 15 cosine 3 times 0.1, which is 0.3. So I key that into my calculator, and out comes the answer. Which is, Robbie, with your new calculator?
Showing the answer is 14.99.
14.99. Agreement there? Check yourself to make sure it's right. Actually, answer should be 14.3. Somebody is going to make that mistake in the exam, I guarantee it. In this situation with wave functions, almost invariably the angle should be in radians. So do try and remember to check that. I know under exam pressure it's tough, and if you do make that mistake, I'll make allowance for it, but you will lose some marks if you. So 14.3. Positive 14.3. So if I look back at the curve, then I must be somewhere along the positive part here. Quite steep, so it's probably up here somewhere, around about there somewhere, I don't know. If I'd worked out the period, I'd have a better idea. Supplementary sort of thought on this. If I had, just think back at these questions for a second. If looking at this original one, y equals minus 5x squared, this one, if I'd added say, a constant to it, say 6, plus 6, if that had been plus 6, what effect would that have had on this curve here? What would effect would it adding 6 have had? Oh, that's handy. Yeah, it would have moved it up, wouldn't it? When x equals 0, then y equals 6. So in other words, it's going to cut when y equals 6 up here somewhere. Does that change the gradient when x equals 2 by shifting it up and down? Does it change the gradient? No. So that highlights why when I differentiate a constant it disappears, because all that does is shift the curve. It doesn't change the gradient, so that's why. And similar in the second question, if I'd add a constant here, plus c or plus 6 or something, all that would do would take this curve and shift it up so that it did that. It would change the values of the function, but it wouldn't change the gradient at a given point. So adding a constant doesn't change the gradient, which is why the differential is 0. Okay, I'll stop that there.